This semester we're thinking of 4 people building the Fender Champ, and it started out as a kit that I bought 10 years ago with some people that wanted to build a tube amp. This is the schematic that it came with, and so we kind of started with that and then just found some problems as we worked through it. So what I'd like to do today is just kind of explain how does a tube work, and there's actually 3 different kinds of tubes that are here, and just kind of explain how those work, and then how each of these pieces does something, and likewise down here, and then next I'd like to talk about some of the testing and measurement of the amplifier and some of its characteristics and why does it sound different than a transistor amplifier. Let's start with the triode. This is kind of a sketch of what it would look from a top view, where you've got a cylinder and another cylinder and another cylinder, except that this grid has got a lot of holes in it. It's really a piece of screen. And inside here is a filament that can basically heat up like a light bulb. And so the filament usually isn't connected to the cathode, although it can be, but usually separated. Then you apply a voltage, an AC voltage to here, usually about 6 or so volts. It heats up the cathode, and you've got some free electrons, or electrons that are moving around or are able to be manipulated. And so we're going to put a positive voltage here. You kind of think of it like a magnet. It's going to try to attract the negative charge that's here. Assume there's no voltage here right now, but you'd have electrons being attracted to the positive battery. You see a flow of electrons, and so you've got a current. Well, you have electrons flowing this way, but our definition of current, or Ben Franklin's, is going in the other direction. Now, if you took this grid that's here, which is a screen, it's got a lot of holes in it, so the electrons can kind of fly through there. And if you put a negative voltage here, you would pretty much push back the electrons that are here. And again, this is like a bigger magnet that's going to pull them through. So as you apply a negative voltage here, you get less current flowing in the tube. And we'll see a picture of what this looks like when you plot voltage and current. If you put a positive voltage here, you would actually attract the electrons. But again, there's holes in it, so it's like throwing a bowling ball and you got a big hole. It just goes right through it and gets collected back up here. So you'd have an increase in current if you put a positive voltage here. But the problem with doing that is that the negative charge would hit this and basically come back this way as a current flowing in this direction. And generally we don't want current flowing in here because it loads down the circuit. So we'll keep the voltage here 0 or negative, and that'll just act as an inhibitor of current for what's going on here. But as we increase this voltage, we can get more current by pulling more of those electrons. Yeah. So that's sort of how the thing works. I'll make all these slides available once we finish the talks. I've got another set I'm working on for the testing. The value of the current that's flowing in the plate over here is also called the anode, is a function of the voltage across the grid to cathode, but also from plate to cathode and another constant or scalar. But it goes as 3/2 power. What that means is that if you had a sine wave here, you're multiplying it to that power, and you're going to create, if you had a sine of a single frequency, you're going to have sines of other frequencies. So that creates harmonic content, and of course that's some form of distortion. So we'll take a look at some of that in measuring what happens. Took some models for tubes from an article by Marshall Leach written some time ago, and did modify them a little bit to make them fit the pictures a little bit better. Marshall Leach passed away about, I think, 6 months ago. He was at Georgia Tech. He did an awful lot of modeling, a lot of audio stuff for a long, long time. I think he's about 70 years old. A really big hole with him being gone. But his website's still there, and there's a lot of stuff in audio that just download and take a look at. He does models of speakers and Pspice and things like that. So I'm trying to pull out some more of this stuff and play with it. And yeah, I used the models that he had developed for some of the tubes, and he has some formulas for how he creates the model. I will talk about how this is done, but just to show you that I can kind of create what the data sheet looks like. This first test circuit is plotted on the next page, and it's plotting the current in the plate versus the plate voltage. Now, this is with respect to the cathode. And I use the same subscripting here as the data sheet did. And as you vary the grid to cathode, I teach electronics, and this is like a JFET, and we use a gate and source, and so I'm going to probably say gate when I should be saying grid, because I don't teach tubes very often. So. But yeah, as you change that voltage and make it more negative, inhibiting for the same value of voltage the amount of current that flows. And this is a picture of the actual tube data sheet, and you can see that it looks similar. It's not identical, but some of the numbers and values here, I've tried to match the currents and the voltages on these extreme ends. And the spacing actually is fairly linear in behavior. So it'll give me a pretty good representation of what's happening, but no model's perfect. But I'll be able to look at this in simulation and take a look at some of the problems I run into, and then maybe look at some modification to the design of it. Pretty close so far, actually. The second curve I did with that second test circuit, and I'll also zip the Pspice circuits if you want to play with them at all, is plotting the plate current now, but as a function of the grid to cathode voltage. You can kind of see how it becomes an amplifier. And this is for different values of DC biasing of the plate to cathode voltage. So if I made that around 300 volts DC, and I had a change in the grid voltage, it would cause a change in the plate current. And that's really what an amplifier is. This is some AC signal, it's sitting on a DC level, and then creating an output that's also sitting on a DC level, but has a change. So I get an output change for an input change. And we're going to make that current go through a resistor usually, and then create an output voltage or go through a speaker. Here too you can see that this same graph was in the data sheet, and it looks very similar. It's this 3/2 power kind of characteristic. There's more detailed models, but this has come pretty close to what I've been measuring in lab with the ones that we've been building. All right, this structure of amplifier shows up twice in the Champ. I thought I'd try to explain it maybe. And again, I did a simulation using the model, and I'll just show you what the results look like. And of course, you collect data and do the same thing too, but when you want to make some changes, and I'll show you a real quick change they did before coming here today, just to see what would happen if I changed one thing in the circuit. I can see very quickly whether it's going to work or not work. I'm also trying to get more power out of the amplifier. I can do some quick changes without having to unsolder or solder things into it. Anyhow, how this thing works is that when you have a DC voltage here, the AC signal is usually, well, the average value is 0, so for DC it looks like a short circuit. And this resistor, I think, is really stuck in here to limit current. So there's really no current flowing in here. If you had again, 0 value for the, here you'd have a current flowing through this thing, and it's going to create a drop across this bottom resistor. With this being 0 and no current flowing in here, what you really have is a voltage across the grid to cathode that's negative. So we actually are biasing it with a negative voltage. And so when you put the AC signal back in, it's going to wiggle up and down. And that's going to cause the plate current to change and create an output voltage here that's sitting on a DC level. We're going to block all that with capacitors. So on the next page is taking a look at the output at that node. It has a DC value, and then it has an AC signal riding on top of it. It's about 30 volts peak to peak. And that's putting in a 1 volt peak to peak signal. So the ratio of those two would be about a gain of 30, or really negative 30. When the input's increasing, the input's increasing, then the current's increasing, and there's, for those that had like 2 or 1 or later, then the drop across here increases, and it's subtracting away from this voltage. So you kind of see things going in the opposite direction. It's creating a 180-degree phase shift. This particular Champ did have a bypass capacitor in. I'll just explain what that is real quickly. When you apply a voltage here, again, there's no current, very little current is flowing here, so this voltage is divided between these 2 elements. Just an equation, you have to work out the actual numbers, but you lose some voltage here. If you put a capacitor across here, and that capacitor looks like a real low impedance at audio frequencies, then you get more of that voltage across here, and the gain goes up. And I've seen versions of the Champ where they put a capacitor across here in that first stage of the preamp, actually. And about, I think, 47 microfarads for pretty much the audio band would give you an increase in gain for the same input signal. And that's what I ran before coming here today. I just put a capacitor and ran the simulation again, and I saw that the gain was 57. So I could actually almost double the gain on the amplifier. I don't double the power out. I'm just going to make it so I don't have to pre-amplify the signal as much. Once I finished building these things, I've been building a little test station in the 303 lab, and I'd like to have kind of one-on-one with you to do the testing on the amplifiers. I'd like to modify them, maybe try this and see how it sounds, and then also measure how much power you can get out of this thing, and then take a look at maybe modifying that a little bit to get a little bit more power out of it. talk some more about that next week. The next thing that was on that first page was a circuit. It's meant to be a tone and volume control. And looking at it without writing any equations, I can see that when the frequency is high enough, this will short out. Capacitors have impedances, as Stephen mentioned, as 1 over omega c in magnitude, where omega is 2 pi f. So as the frequency goes up, the impedance or effective resistance goes down. So at some point, it lets the signal come through here and get divided out. So at high frequencies, I've got some change in sound. So that could maybe be something with treble. And then same thing here. This could also become a short, eventually become a short. And I've got some manipulation in the size of the signal. So it seemed to me that that would probably, work as a tone control. But when we first built these things, none of them, when we varied them, did any tone control. And I thought maybe we miswired something, but then I simulated it and found the same stuff. I did a little bit of a hand analysis on it and found the same thing. So I started redesigning this a couple semesters ago and came up with roughly this circuit. But then I did some searching and I realized that there was other versions of the Champ. One was called the Princeton Champ, and actually used this circuit with pretty much the same values that was up here. So I'm not sure the guy that was selling the kit either drew the schematic wrong or what, but this definitely will have some tone changes. So what happens with this one is that this becomes a short somewhere at the beginning of the audio band. And then, so I got my signal coming in from the first preamp stage, and then I got a division here, so I get some voltage out, up or down in terms of loud or soft here. And then actually this one shorts next, about maybe around a couple hundred hertz or so, and that puts a resistor in parallel with this one and causes the volume to change. So at some frequency, the volume is now different, so you can get a boosting or a cutting in the sound. And then a little bit higher in the audio band, maybe about 4 or 5 kilohertz, this thing becomes a short relative to things that it's in series with. And you again get another path back to ground here, so this resistance here now is put in parallel, actually with this what's over here, so it changes the value of the resistances. So it does cause the volume to change with frequency. But volume and tone are actually mixing together in their behavior, so when you're varying one, you're actually varying both of them. And I'll run some simulations on this in the second part of the talk next week. Then there was another one of these, let me go back this one here. It's called a common cathode circuit, but actually that's with, when you put this capacitor in here, this becomes a short to ground for AC. Again, it's a pretty big capacitor, and so the cathode is common between the input and the output, so we call it a common cathode amplifier. But here it doesn't have the bypass capacitor, but putting it in on that first preamp will give you almost double the gain, if you need to have that kind of gain. Now the next amplifier had another type of a tube that's called a pentode. It's got 5 elements to it. So I've got the grid again, I've got the cathode. Filament heats up the cathode, gets the electrons moving around. And usually this is likewise negative as it was before. Let's just think of it as 0 volts for right now. And again, it's got a lot of holes in it, so whatever electrons come flying at it, most of them can go right through it. There's another screen that's added here. Likewise too, it's got a lot of holes in it, and this is usually held at a positive voltage. And what happens here is that this positive screen attracts the electrons that are here because it's a shorter distance, so it kind of gives them some momentum. So they come flying at this screen and just go right through it. This next screen is called the suppressor screen. It's actually tied back to here, so it's negative potential with respect to ground. And some electrons are going to be repelled by that, but they're going fast enough, they just go right through the screen and then hit the positive voltage that's up here, with really like a big magnet. The reason this is stuck in here is that when those electrons hit this, sometimes they knock loose another electron that bounces backwards towards this positive screen that's here, and so it would actually go current in the opposite direction and lower your current. So you put the suppressor in, so if something bounces off of here, this repels it back again. So okay, so that's what's going on with that. Then as you vary this voltage here, you inhibit those electrons, and so the current goes down. The curves you get out of this one are quite different than the ones we had from the first two. Oh, one more thing here. The relationship between the currents that are flowing, the screen and the plate, have to do with a scalar with this equation stuck in it. So again, it's a function of the grid to cathode, but now the screen to cathode and the plate to cathode has again a 3/2 power. This has more distortion than the triode does. And so we're going to use some feedback techniques to clean it up. So this first file is running, again, one of the pictures of the voltage and current of that tube. I'm just going to compare it to the data sheet to show you that it comes pretty close. So you get a family of curves here, and you can see that they're, for the same change in voltage, they're not equally spaced. So that's going to represent a change that's not uniform. So it's a form of distortion. And then here's the picture out of the data sheet. There's something else plotted here for the screen current. But you can see that the shape of the curves is similar. It's more rounded in here than what was here. And later models, people did a better job of fitting this. But this will begin to do the kind of things that are down here, just kind of in, in a generic kind of form. But you can see here too, as the grid voltage is changed, as it's made more negative, the current goes down for the same value of plate voltage. As you increase the plate voltage, you increase the current, but not by a lot. And this looks very much like a transistor type curve. Those that are in 302, we're about to talk about a JFET, and that's what the curves look like. It's similar to a BJT, except that voltage is controlling instead of current. There's very little current going into the grid. And then the second curve is plotting the output versus input. The same circuit, but just varying a different parameter down here. And what I'm getting for that is the plate current as a function of the grid voltage for different screen voltages. So you can play with that too, and you get a curve, and if you had a change in the grid voltage, you get a corresponding change in the plate current. We'll make that current go through a resistance, and we can actually create a gain. So an input is controlling an output. And you can see how that matches the curves that are here. Pretty close. I just play with the numbers to try to get some of these endpoints to fit. So I've got something that's pretty much in a pretty good ballpark. This looks pretty good compared to this. The last one was a little straighter than the actual curves are. But you can find models that'll do a little better job of it. Another thing that's in that next circuit is a transformer. The voltages that are needed to operate the tube are a couple hundred volts, and I don't want to really bring that out to a regular speaker because that's way too high. And so this device takes voltage and can step it down. And so the ratio of this voltage to this voltage, if it's a perfect transformer, is a turns ratio. Now this could be a number 1 or greater, or it could be a fraction, like a half or a third. And then the currents, the coming in and going out, you go at their ratio in just the opposite direction. If you take n here and take the reciprocal of this and set it equal to this, you'd have I2 over I1 over I2 is equal to n. And so if you cross multiply, you'd have I2 times V2 equals V1 times I1. What that's saying is the input power is the same as the output power. That there's no, in a perfect transformer, no losses. Also, the turns ratio is the square root of the actual inductance that's here on both sides. What we're getting is a change of voltage and current, and so you effectively change the impedance levels. So if you got a speaker hooked up here, the impedance looking in here, you derive the formulas up above. This is in the 202 notes for those that are in the EC program. The impedance looking in here is this load divided by n squared. So you change the levels. We're going to actually make this like 1/45th. And so we're going to have an impedance looking in here that's much greater, 45 squared times 8 ohms. So what the tube sees is a much higher resistance in this case. And then the voltage is stepped down, but the current is stepped up. So this is how this works. If the voltage goes down, the current will go up because the power in equals the power out approximately. Let's put all this together. And so this is this pentode output state. It does have the bypass capacitor in there. And so I ran the simulation and just to see what it would do. You can also analyze this with formulas, but I thought this may just be a little bit easier just to measure it. Okay, so the output is 11.3 volts peak to peak. The input's 12. So the ratio, and there's also a phase change here too. So the gain is approximately minus 1. So it's giving me a voltage gain of 1. So that doesn't sound like it's going to be very useful, but actually what this is used for is for current. So if you look at the current in the load, it's on the order of a couple hundred milliamps. This tube is operating also in the hundreds of milliamps in value compared to the triode, which was in the couple milliamp range. So this is used for boosting power levels. But if you take a look at the current that's coming in, it's very small. Ideally, it's 0. In the model, there's a resistor and a diode stuck in. I haven't measured this current. I'm not sure if this is super accurate. But if it is, you have a current gain that's on the order of 94,000. But ideally, if this is 0, the current gain is infinity. You're getting a lot of current out for very little current in. That's because the voltage is controlling the flow of current. So this is really a power amplifier for boosting the current in the outputs. The two together, this common cathode, amplifier, although there's not a bypass here, and then this pentode amplifier form an op amp for those that are in like 201 or 202 or later. The spacing on these curves is much more non-uniform than they were on here, so there's quite a bit of distortion. So we put two amplifiers together, the overall gain of these two, there's some loading between them, is roughly the product of their gains. So you get a gain of this amplifier, something on the order of 28 or 30. That's not a big number, but if you have like 201 or 202, you might see this formula in my notes or in the textbook too. And that's for a non-inverting amplifier is what this is. Here's your op amp, and here's your feedback resistors. If this has a huge gain, it's 1 plus this resistor ratio. But really what the formula is this, where if A is a huge number, then this term drops out. You just have 1 divided by 1. And it's a function of the resistor ratios. You'd have to add more tubes to get this to be bigger, but using the value of 28.43 here, and the resistors, I would predict that this has a gain of about 10. I just go measure it and see if it's coming close to that. Actually 9.675. I did that, I ran the simulation of the two together, gave it the transformer, some values that measured off the transformer. And so here's the output. It's actually 9.18 volts peak to peak for a 1 volt peak to peak input. The gain is 9.18. Just ignoring the loading effects between those two amplifiers. So what I've got is the ability to increase the current in the load, and that's what that stage is used for. And then the feedback factor here reduces the overall distortion. That the gain is determined roughly by the resistor ratio plus 1, although it's a little bit off because this number isn't huge here. It's just, you know, in the order of 30 or so. But the reason they're putting this feedback around is to get rid of the distortion of the pentode. The triode isn't as bad as that one, but it's a way to lower the distortion. I'll measure some of the distortion in the actual amplifier with some equipment we have in the lab, and we have a little lab experiment we can do some testing on amplifiers. The last element is on the bottom of the schematic. Let's go back to page 1. So here is this common cathode amplifier. Here's the op amp. It's got a common cathode amplifier, gain around 30 and then gain around 1, but I've got a current gain that's huge, so I can drive a load that's out here. And here's my feedback paths that are here. And then down here is the power supply. And so what I've got is a diode, actually 2 diodes. The diode usually has a filament connected to the cathode. And the same thing, we're going to heat this up and get electrons to be flowing. And then if you apply a big enough voltage here, you'll attract those electrons once the voltage gets to be large enough, and the larger the voltage, the more current that you'll get. So you get a curve that looks like this. This is, if you had a diode, like if you're in 302 or playing with diodes, they kind of have a curve that looks like this, but the ones we've got with silicon diodes, it's about 0.7 and it goes straight up. So this has got quite a slope to it and really quite a large drop across it. So we lose quite a bit of voltage across a vacuum tube diode. So in that amplifier, we're using a diode for the power supply, but in the hi-fi ones, we're using a bridge rectifier with silicon diodes. The tube diode has a response time. So when you overdrive the amplifier, the tube can't respond fast enough, so it actually creates a sound effect. And so I've seen this in some of the testing, not made a sound by watching the power supply trying to catch up to driving an output. And tell me that that's something that you can play with when you're playing the guitar. I don't know if it is or not. But yeah, what's in that diagram for the power supply is actually 2 diodes. And the way this works is that the voltage is between here and here, and suppose that voltage is positive, it's the top part of the sine wave. So we're actually going to step the voltage up from the wall outlet. We're going to make it bigger by a factor of 3.1. So you get 170 volts peak or 340 peak to peak. We're going to make that 3 times bigger. Okay? The reason for making it so big is I'm going to drop some voltage across that diode, not like a 0.7 silicon diode, maybe 100 volts or more. So what happens when the voltage is positive, current can flow this way back to the load and back to the ground this way. But current can't come back this way. It can only go in this direction. It's got a one directional thing. But when this goes negative, this is also negative, and then current can actually flow in this direction back to ground this way. So I get both parts of the sine wave. When it's going positive, the top diode conducts, and when it goes negative, the bottom diode conducts. And you actually get what's called a full wave rectification, taking that sine wave and just flipping it over and getting a fairly large voltage at the output. Again, I've lost a lot across the diode. Because what I've got is a 170 volt peak times 3. What I'm getting out is around 300 some volts. Again, these are very lethal voltages, so be very careful, and we've got the bottoms actually sealed off and we give the amplifier back to you. Now, if you use this for a power supply, the voltage collapses every 8 milliseconds, and it would sound horrible if you look this up as a power supply for the tubes. The trick is to put a capacitor across it to make it smooth it out. Putting that in there, you can see what happens to the previous picture. It kind of smooths out, and there's a little bit of a ripple in it. The bigger that capacitor, the smaller that ripple will be. And I begin to get more constant voltage again, something on the order of 300 volts or so for powering the tubes. And lastly, that's kind of putting it all together then. So here's my first common cathode amplifier with a gain of around 30. I've got a tone control here. I'm actually going to replace with a different tone control when I do the next forum, which is the one that's in the Princeton Champ. This actually does do volume control, but very little tone changes to it. And here's that op-amp, non-inverting op-amp with the feedback resistor. And then here's the power supply with that first capacitor that I had, but actually put another capacitor, and it smooths out that ripple that's showing up over here. And so the voltages here, I actually used to use some of the biasing of the tubes to get a cleaner power supply. That ripple that's over here is actually only used on the output transformer side, but in the other one's a much cleaner signal. So we'll take a look at next time is take a look at a simulation of the whole thing working together and actually look at some of the nodes, and then do some testing in Pspice, but then do physical testing and compare the two side by side, and then talk about maybe making some changes to the amplifier and seeing if we could, say, increase the gain, as one is to add this bypass capacitor, or can we change some of the biasing of the tubes to actually get more power out of the amplifiers. We'll take some measurements on that with simulation and then physically, and then those that are building it will follow that up with some stuff in the lab. Yeah, that's a kind of a block diagram approach to how that champ is working. No formulas in terms of solving more models and things, but just simply measuring the gains from stage to stage and watching what's going on. Do you have any questions at all? Yeah.
Someone who doesn't have any classes in lab, what program do you use to analyze these?
It's a program called Pspice. Pspice is an acronym for Simulation Program with Integrated Circuit Emphasis. It was written to save the cost of designing an integrated circuit. It cost a couple $100,000 to make the first chip. The second one maybe cost you a nickel or a dime. But if you screw up the first one, you have a lot of expense. And so the group at Berkeley that wrote some software that would do the nonlinear differential equations, and it was really used to help design integrated circuits, but we can use it for vacuum tube modeling. I had a friend that was at U of M. He was modeling washing machines for Whirlpool using Pspice because you can do electromechanical equivalent circuits. It's very easy to use, and you see the format was there. It's kind of describing what the schematic looks like. And the equations are either built in or stuck into the modeling of it, either built into the software itself or what are called sub-circuit models. And then you can play that back and see what happens as you do it. So it's not, it doesn't get you everything, but it gets you kind of closest to what's going on. And you don't have to build everything first, but you can do it on a simulation to see, well, is that roughly doing what I want, or why is this happening? Or what if I could take this capacitor out, but in lab I really can't because it doesn't work anymore? Or I can change the size of something. So you can do a lot of what-ifs with the simulation. So that's what we'll do next. We'll take a look at some testing, and then I'll do some physical testing to see how close it comes and how close the models come. And if they don't, then I go back and iterate the model. So the model you can see is close, but not exact. But does it come close to predicting what I get in lab? If it does, then okay, I'm close enough, and I'll just kind of work with that. Yeah, all right. Did you follow?
Is there a copy available on?
Yeah, there's a free version. In fact, it's at workad.com.
Okay.
Yeah, I can give you the link if you want.
Okay. I think the computer's downstairs, right?
Yeah, it's at all the computers here. We have a full program. The student version is the same program, but limited to about 50 elements.
Okay.
And all this could have, well, I'm not sure if this one we're going to run on the student version, but pretty close to it. Yeah, right.
So I'm looking at the part right before it goes to the 12AX7 with the resistors and the capacitors down near the bottom, and the fact that having the resistors between those capacitors, does that mean that the waveform smoothness changes with frequency?
Yeah, well, it's called a low-pass filter.
Right.
And so I've got some initial filtering here, but I see I have that ripple there, and then that has a frequency component, and then this R and C, if you ignored this, would actually filter out some of those components and then get rid of that rippling that's there, and then they do it one more time. And so what comes out of here really looks very flat. And so that's fed back to here, which is where I'm getting my biggest gain. And any kind of wiggling up here would just come right through, and you'd hear it in the speaker. So that rippling you saw here, wouldn't want to feed that back over here. You'd actually could hear it, even though it's not real big, but it's at 120 hertz roughly. And so these filters are literally pulling that component out. It's letting the low frequencies below 120 hertz through, but above it is blocking it, essentially making it like a voltage divider, making it smaller.
So how efficient is this? Like, how much are you losing?
Oh, this is horrible, actually. This is 25% maybe efficiency. It's, yeah, this is you wouldn't want to battery operate these things. But that's their main disadvantage, is that they're not very efficient. They are capable of enormous power outputs. Transistor, they got several hundred volts across here. Transistors are rated in the 40, 50, 60 volt range, so it's, you got to play tricks and games to get bigger signals out. So if you have to get really a lot of signal out, a tube is one way to do that. But it also sounds different than a transistor for a reason we'll talk about next. Jeff was going to play, actually. Let me just tell you what's in the box is a 12-inch speaker, and I hooked it up to the tweed and put the tweed inside the box, but I made it so that I could disconnect the speaker so I could plug in our other amplifier, so you can hear what it sounds like with a 12-inch speaker. And this is a Weber Pinto.